Okay, in this video I'm going to present to you the next laboratory exercise called conservation of energy. For those of you enrolled in Conceptual Physics AB, you will complete this as a mini lab exercise. For those of you enrolled in Physics AB, Honors Physics AB, and AP Physics C, you'll analyze the data that I'll obtain here in a formal laboratory report. The purpose of this exercise very simply is to verify that energy is conserved for an object in free fall. So I'm going to use a spark timer to obtain the data that we'll need for this experiment. Here's what I'm going to do. I'm going to take an object here of mass equal to 1/2 kilogram, and I'm going to attach a piece of strip tape to it, and then I'm going to thread the strip tape through my spark timer. So let me go ahead and do that. So I'm obtaining here a piece of the strip tape. I'm going to thread that then like so through my spark timer, and then I'm going to tape it to the object like so. Okay, and then I'm going to start the object here initially at rest, and then I'm going to drop it from rest like so. Like so. Okay, let me make sure that I obtain the data that I need here on my tape. Like so. Okay, this is going to be a good tape for me to use. Okay, let me go ahead and put this off to the side. I will photograph this tape for you in today's folder such that you could obtain the data from it. Okay, let me go ahead and tilt my phone back towards the board, and then let me go through the laboratory exercise with you. Okay. Like so. Okay, so let's go ahead and now get to our laboratory exercise. So our lab is on conservation of energy. The purpose is to verify that energy is conserved for an object in free fall. Okay, there's a little bit of theory here behind the experiment. For those of you that are writing a formal laboratory report for this experiment, you have to show this theory in the first section of your report. Okay, so first of all, we have right here an object of mass m equal to 1/2 kilogram. And then as you saw, I attached a piece of strip tape to it like this. I then threaded the strip tape through my spark timer. Here in green is my spark timer, will say. Here are the prongs associated with it. And then what I did is I dropped the object from rest. We're going to specifically say, however, that we dropped the object from rest at the origin. So let's consider this here as the origin like so. If I drop the object from the origin, what I'm saying is that I'm dropping it from height 0. And I'm also dropping it from rest. So if I drop it from height 0, this then means by definition that the potential energy is equal to 0. And if I drop it from rest, the kinetic energy is equal to 0. So then therefore the total energy E of the object, which is always kinetic plus potential, is equal to 0 plus 0, it's equal to 0. So by definition, I'm saying that the total energy E of the object is equal to 0. Therefore, as the object falls, and I calculate the kinetic energy and potential energy as it falls, the two numbers added together should always be the same thing, a total energy of 0. Now, how can a moving object have a total energy of 0? Well, as the object falls, it gains kinetic energy as it does. But if it's falling below the origin, I then have to think of the potential energy as a negative number. So the positive number for kinetic energy will cancel out then with the negative number for potential energy, such that the total energy E is equal to 0 the whole time. That's the theory behind the exercise. Okay, now let me go ahead and get to the procedure. Okay, so with respect to the procedure, as you saw me do, I then attached the object to a piece of strip tape. I then threaded the strip tape through the spark timer, turned on the spark timer, and then dropped the object from rest. Make sure, of course, you give me a basic description of that in the procedure section of your laboratory report. And then ultimately on my tape, we have the following. Okay, first of all, at the beginning, there's a little bit of smear. This corresponds to the time between me turning on the timer and actually dropping the object to the floor. But then as the object accelerates towards the floor, the dots, of course, get progressively further and further apart. Okay, now, specific to this lab exercise, I have to choose the very first legible dot after the smear as my origin, as dot 0. The reason for this is because what we are assuming is as follows. We're assuming that the object starts from rest. Therefore, I have to choose the first legible dot after the smear as my origin. So choose the first legible dot. Okay, and then I number out from that 0, 1, 2, 3, 4, and so on, ultimately out to a dot 9. So I once again have 10 dots to work with. Okay, and then we get to the data. The data table that I'm about to describe is identical to the data table that we saw for the laboratory exercise involving free fall back in our unit on kinematics. We have the following. Okay, there's going to be 4 columns to the data table. Okay, the first column is the dot number, which if you recall, we refer to as the index letter N. N is equal to 0, 1, 2, 3, 4, and so on, ultimately up to a dot 9. Okay, then we have the position of the nth dot in terms of meters, where dot 0 is our origin. So then therefore you measure from 0 to 1, 0 to 2, 0 to 3, and so on. You can measure in centimeters, that's fine, but make sure you divide by 100 to convert to meters as you tabulate. Okay, and then the next column is the time at the nth dot in terms of seconds, where dot 0 is when we start the clock. Because 60 dots are made per second by the spark timer, the time at the first dot is 1/60th of a second and 2/60ths of a second, and so on, just like we've seen in some other lab exercises already. And then the last column is to calculate the velocity at the nth dot in terms of meters per second, and once again we use the following formula to do so. So recall this formula from previous lab exercises. Like so. And then recall the example that I always illustrate to describe the use of this formula. For example, let's say that we have to find the velocity at the 6th dot. So what you then do is you take the position of the dot ahead of it, the 7th dot, subtract from that the position of the dot behind it, the 5th dot, and then you're always dividing by the same thing. You're always dividing by 2/60ths of a second. Recall, however, the shortcut. Instead of dividing by 2/60ths of a second, you could take the numerator of this expression and multiply it by 30. Remember, however, that you can't use the formula to find the velocity at dot 0 because we don't have a dot -1. Normally, then, what we would do is put a slash here for the velocity at dot 0. Not so, however, in this case. We're assuming that the object starts from rest. Therefore, we have to put the initial velocity at dot 0 equal to 0 for that reason. However, you still can't use the formula to find the velocity at dot 9 because you don't have a dot 10. So then therefore go ahead and put a slash there. So far this data table here is identical to data tables that you've already seen with these spark timer laboratory exercises. And now we get to the analysis. The analysis is basically just 3 more columns to this data table. If you have room on your paper, you can go ahead and write those columns with this data table, or you can just make a new data table. That's what I'm going to do here. So I'm going to erase. And now let me call this the analysis. What I'm going to draw is 4 columns. Okay, just for reference, the first column I'm going to once again call dot number n. 0, 1, 2, 3, and so on, up to dot 9. And now we get to these new 3 columns. Okay, the first of these 3 columns is the kinetic energy at the nth dot. The kinetic energy at the nth dot in terms of joules. Here's how you find it. The kinetic energy at the nth dot is equal to 1/2 times the mass multiplied by the speed at the nth dot squared. So what you do is you take 1/2 times 1/2 kilogram and then multiply by the speeds squared. When you do, you end up then with the kinetic energy in terms of joules. Now recall that the speed at dot 0 was 0. Therefore, the kinetic energy at dot 0 is equal to 0, and then you make the calculations for kinetic energy for dots 1 through 8. You can't do this, however, for dot 9, remember, because we don't have a speed at dot 9. So you do this for dots 1 through 8. When you calculate the kinetic energies, they're going to be really small numbers. Don't round them off. Go ahead and tabulate the entire value that you see on your calculator display here in this column. Okay, and now we get to the potential energy. The potential energy at the nth dot, also in terms of joules. How do you calculate the potential energy? Well, remember that the potential energy is mgh. H, however, the vertical change in position, is the same thing as the distance x that we calculated or measured earlier rather, and already put into our first data table. However, as I said earlier, we have to think of the potential energy as a negative number. So then therefore you calculate the potential energy U as negative mg times x sub n. So you take negative a half a kilogram times 9.8 meters per second squared times the positions that you had measured earlier in the earlier data table. However, for dot 0, remember that the position was at 0, therefore the potential energy at dot 0 is equal to 0. And then you calculate this for dots 1 through 8. Don't bother doing this for dot 9, however, because we don't have a kinetic energy at dot 9 anyway. Once again, the numbers will be small. Don't round them off as you tabulate here in this data table. Write down everything that you see in your calculator display. Okay, and then the last column is the total energy E at the nth dot in terms of joules. In order to calculate the total energy E, you just add the two columns together, kinetic energy plus potential energy. So notice for dot 0, we have 0 plus 0 is equal to 0, like so. And then if you do this for dots 1 through 8, it should be equal to 0 the whole time. Basically, the positive number for the kinetic energy should cancel out with the negative number for potential energy to give you a total energy E of 0 the whole time. Once again, however, don't do this for dot 9 because remember that we don't have a kinetic energy at dot 9. Now, due to qualitative sources of error, when you calculate the total energy E, of course, it's not going to be 0 the whole time. So then therefore, how do you know whether or not you got a good result? That's where the graph comes in. Okay, for the graph for this laboratory exercise, you're going to put 3 pieces of information on the same graph. Here's how you do that. Okay, first of all, the horizontal axis. You're going to draw this in the middle of the piece of graph paper. As is always the case, is the time in terms of seconds. So we have 0, let's say skip a space, 1/60th of a second, skip a space, 2/60ths of a second, and so on. And then, on the positive side of the vertical axis, this is where you're going to plot the kinetic energy in terms of joules. Based upon the numbers that you calculate, it's going to be up to you to figure out how to scale your axis. Now, when you do plot the kinetic energy, you're basically plotting this equation, which is a speed squared as a function of time. So you're not going to get a straight line. Instead, you're going to get something that looks like a parabola. Don't connect the points, but the points should very noticeably look parabolic. It should look like this. Like so. Okay, and then on the negative side of the vertical axis, this is where you plot the potential energy, also in terms of joules. Now, when you scale your axis here on the negative side, make sure that you scale it exactly the same way as you did earlier on the positive side. So on the positive side, if you said like 0.1, 0.2, 0.3, and so on, do the same thing on the negative side. Negative 0.1, negative 0.2, negative 0.3, and so on. Make sure that you scale the axes the exact same way so you can see the symmetry on the graph. Okay, now, when you plot the potential energy as a function of time, basically you're plotting the position of a falling object as a function of time. Therefore, it should also be a parabola, in this case a parabola that opens downwards. That is like so. Once again, don't connect the points, but the points themselves should be very obviously, noticeably parabolic. And then, as you might guess, the last piece of information that you plot on this graph is the total energy E. Because the total energy E should be 0 the whole time, when you plot those points, you should basically see a line, like so, along the axis. This is what we're looking for on the graph. We're looking for the total energy E basically staying very close to the time axis as time goes on. If your values of E stay very close to the axis, then that's a good result. We're not going to calculate a slope here. We're not going to calculate a percent error. We're just going to qualitatively interpret your result. There are, however, a couple of errors that can happen. So in the error analysis of your individual laboratory reports, I then want you to describe the following if necessary. Let's say, for example, that when you plot your total energy E, it doesn't stay very close to the axis, but instead you see a general trend downwards like so. In other words, as the object falls, it's somehow losing energy. It would do so due to friction. Friction between the spark tape, for example, and the spark timer would cause some of the energy to be lost as heat. In addition to that, you may see a slight positive number to your total energy the whole time. Why would that be? What about the laboratory exercise would cause it to look as if there is extra energy present? Well, remember what we're assuming about the velocity at dot zero. We're assuming that the object is at rest at dot zero. That's not necessarily the case. It's already moving a little bit after I've let go of it. Therefore, there's a little bit of extra kinetic energy there that we're not taking into account. So if you see a slight positive number to your total energy, it is for that reason. So based upon the result that you obtain, interpret that result correctly in error analysis.